video solution for E&M 1 final take-home exam. Video solutions on number 5. Number 5 says, with an appropriate choice of coordinates, if we can model a polarized hydrogen atom as having the charge distribution rho of r equals q times the delta function of r minus r naught z hat minus q over 4 pi e to the negative r over lambda divided by lambda squared times r. Part A says calculate the monopole contribution to the potential, and does this agree with your expectations? So part A, monopole contribution, we have V for monopole is 1 over 4 pi epsilon naught times the total charge divided by the radius. So the total charge would just be the volume integral of the volume charge density over d tau. So that's going to give you two separate integrals, one with the step function and one with the second part here. The step function is just going to integrate to give you q, and the second part, if you pull out the q over lambda squared, you can integrate from over r from 0 to infinity of e to the negative r over lambda times r dr, and that's just going to give you lambda squared. So these lambdas cancel, you end up with q minus q, which is 0. It does, it is what we expected, because in a hydrogen atom there's only one positive charge, one negative charge. So when you add up the total charge between them, the answer is just going to be 0. So because that is 0, the potential, the monopole contribution to the potential is also 0. Part B says calculate the dipole moment. Alright, well, since it's once again just a positive particle and a negative particle, the dipole moment is just that of a dipole, which is just q times d, where d is the distance between them, and it'll be in the r hat direction. Part C wants to know the potential of the dipole, so plugging in this to this equation, we end up with 1 over 4 pi epsilon naught times q times d over r squared, and that those two r hats cancel out to just give us 1. Part D, the last part, says calculate the exact potential and compare your results from part C and D. Is the dipole potential a good approximation to the exact potential at large r, small r, everywhere, nowhere? So using this equation, V of r equals the integral of rho of r over script r d tau, we can calculate the exact potential. R is going to be equal to r hat, r prime is going to be r naught r hat. Script r is going to be these two minus each other, so r minus r naught in the r hat direction. And magnitude of script r will end up just being r squared minus 2r r naught cosine theta plus r naught squared to the 1/2 power. Plugging this in and the volume charge density into this equation, we end up with 1 over 4 pi epsilon naught volume integral of q over script r, magnitude of script r times the step function over d tau, minus q over 4 pi lambda squared times the integral of e to the negative r over lambda over script r d tau. Then what happens after that is this step function integral here ends up just giving you q over root 2 r naught. And then this other part, ends up just giving you negative q over 2 pi, or 2 lambda squared, integral from r equals 0 to infinity of, after you integrate over theta, it ends up giving you r plus R naught squared square rooted over R naught minus the same thing except with a minus sign, all times R dr. Now when we look at this guy, we have to be very careful when we take the square root of this square, because we'll end up with two cases, one for inside the atom and one for outside the atom. So we have to take plus or minus this, and the minus case corresponds to the outside potential, exact potential, and the plus case corresponds to the inside exact potential. So what we actually end up getting for those, V out equals Q over 4 pi epsilon naught times 1 over root 2 R naught minus Q over e to the R naught over lambda times this times the quantity 2 lambda squared times 2 lambda R naught plus, or 2 lambda squared plus 2 lambda R naught plus R naught squared. And then for V in, we end up with Q over 4 pi epsilon naught again. Step function stays the same, and that's minus 1. First off, this up here should be a 1. And this one stays the same as this one still. And this term ends up being negative lambda over e to the R naught over lambda minus R naught over e to the R naught over lambda plus lambda. And then comparing those answers, I have at large R, both the exact potential and the dipole moment go to 0, so it would be good approximation at large R. At small r, it goes to a very large potential, so it is a good approximation for inside the atom. However, it is not a good approximation for potential near the edge of the atom, because these would give you a much more accurate answer than this one.